What I wanted to look at here is a moving charge in an electric field. And again, how are we going to do that? Well, we'll do it with our trusty capacitor. Now, positives at the top as usual, negatives at the bottom as usual. Drawing our electric field from plus to minus. But this time, our trusty little electron. Now, let's make it a proton. A little proton has got a velocity like that. Forget about gravity. We've got no gravity here, okay? Now, it's a positive charge. So as it enters the electric field, it's going to feel a force in the direction of the field lines. In other words, down, all right? So what motion is this going to have? Well, it's horizontal velocity, and that's all it's got here. VH is not being acted on because there is no horizontal force. There is just a vertical force. So this very much becomes just like the parabola when we have a ball or whatever, a projectile, and it goes up, right? What happens is we get a parabola. What we've got, our horizontal is staying constant, and our vertical is being acted on by a force, and the force remains constant, and that gives us a parabola. This is what happens here. Our horizontal is going to stay constant. We've got a vertical force that's going to act to accelerate us. So the motion you're going to get is one that looks like that. All right, now the force, and that is a parabola. Now, does a moving charge create a magnetic field? Yes, but we're just ignoring that at the moment. A moving charge does create a magnetic field, and the magnetic field would just be around, it would be around it as we have experiences, circular, perpendicular to the direction of motion. All right, enough on that little bit. What else? Where do people go wrong with this? F equals EQ. I said the electric field in here was uniform, therefore never be thinking that the force is greater the closer you get to the negative plate. It's not. It stays constant. Now, when force is constant, acceleration is constant. Force is constant, acceleration is constant. All right? Remember that. That's very important. So I see this is the kind of problem we see all the time, and you often have to draw that sort of effect. Is this a gain in potential energy or a decrease? Well, if it's moving with the force, which it is in these examples, then it's a decrease in potential energy. Therefore, no increase in potential energy. All right. What other type of problem do we get with these ones? I'll just do it reasonably quickly because these are quite simple. We sometimes have the problem where you've got a charge and they give you its mass. Now, say that's a positive charge. Now, a positive charge with a mass, I don't know, we could say the positive charge has a charge of, 3.2 times 10 to the, minus 9 coulombs. All right? Quite a big charge. Now, it's got a mass. We could say its mass is 1 microgram. Now, the thing is that this is going to experience, it's a mass, so it's going to experience a weight force. Weight force is always mg. Don't be tripped up when you do these calculations, all right? 1 microgram. It's not 1 microkilogram. So when I go to convert 1 microgram into kilograms, I have to convert 1 microgram into grams would be 10 to the minus 6, grams into kilograms, 10 to the minus 9. So if I was to write the weight force on that, it would be 1 times 10 to the minus 9 times gravity, 9.8. And that would be the weight force. Now, that one trips me up. That one still gets me sometimes. I forget that it's in grams. So I just do the micro 10 to the minus 6 and I get it wrong. Silly me. All right, so what they want you to do in this case, though, is they want you to be able to suspend the charge. So we need an equilibrium of forces, and the way we do that is by having an equal and opposite force up, like that. So we have to make the two forces equal. So that means mg must equal EQ, because we need an electric field in there. And to get a force on a positive charge up, we would have to put our positives down on the bottom. So they may ask you to put the polarity in to get that correct. And then they might ask you to solve this equation. You've already worked out mg, you've got the charge. They might ask for the strength of the electric field. And in a tricky one, okay, so you've worked out the strength of the electric field, right? They may have given you the distance here, and they may now want you to calculate the voltage on these plates. And you'd have to draw maybe the polarity on these plates. So we'd need a battery that puts positives down here and negative here. And we might then have to do that equation where we go V equals ED. We've got E, we've got D, we need the voltage. That's, again, a common type of problem for this type of work.